So let me go now to Mike Gamble, a man who needs no introduction. Mike has been with us many times. Mike Gamble is semi-retired from a career position at the Boeing Company, where he worked on a wide range of classified and unclassified programs, including commercial aircraft, military aircraft, and aerospace systems. His role there was managing the Boeing Research and Development Lab, working on a variety of traditional exotic aircraft and aerospace technologies. He is going to present an analysis for us comparing mechanical to electrical methods of propulsion, synchronized rotating systems, and electromagnetic equivalents, and covering a few types of Dean drives, rotating mass systems, comparing mechanical and electrical methods and equations, and showing the electrical equivalent systems to a Dean drive, along with proposed electrical propulsion systems based on those equations. So this is something that Mike has been working on for a while. This is kind of a successor to his last one. Let me ask Mike to unmute.
Can you hear me?
Yes, welcome, sir.
Yeah, if you want to take a little more time on questions there, this is a short one, only about a half hour. So if you want to go a little further on questions, I got no problems.
Oh, well, I already did the introduction now, though.
Well, no problem. We can take it from here.
Oh, okay, yeah, no, if you'd like to, sir, go ahead.
Okay. Let's see, we got to hit, I got to bring it up and then hit share screen.
Yeah, and we do hope to have Jason back, especially to talk about the SEG, because he's a pivotal part of the SEG team. He's worked with John Searle and Fernando Morris and a lot of different stuff. So yeah, I appreciate his time, and I would love to have him back. But I'm really excited to hear about the Dean Drive presentation as well, because this builds off of a lot of your earlier work.
Well, that's the reason I had an order to him that I wanted to pitch him in, for that very reason.
Well, and thank you for presenting.
The next two, I got two more in this series. The order is also there.
Okay, so let me put myself on mute. I can see you just fine with your slides.
Okay, I'm trying to get, I think we got them up. It's okay?
Yeah, it looks great. Let me mute myself out and you can get started.
Okay. This presentation, it's got a fancy title, Support Forces in Synchronized Rotating Spring Mass Systems. That's just a fancy name for Dean drives. This particular one was co-authored by Chris Profadius. And of course, I have the disclaimer here that allows it to be Boeing memo that allows release of this document, so you guys don't get in trouble over it. That's pretty much standard in my Boeing stuff. This one, the presentation is an extract from the paper. There is a paper that exists that we wrote with the same title. The co-author, Professor Christopher Profadius, is from the National Technical University of Athens, Greece. And I met Chris at the 2011 SPESIF conference, and we decided to put our heads together on this paper because we had similar interests on Dean drives. The problem we hit was he's Greek and I'm American, and there was many issues that had to be resolved with Boeing to get this paper out the door. As a matter of fact, we were accused of being spies. They locked our computers and deleted emails and that to find out what was going on, because it looked like I was sending him classified information because we were writing back and forth. He'd write, I'd edit, I'd write, he'd edit. And pretty soon they got suspicious, so we had a big round there. But anyway, they finally let it out the door. Okay, we'll start with here, Dean drives. They're basically proposed propulsion systems based on the principle of rotating mass. And we have a couple of different implementations of those principles we can show you here. We start with the theoretical model of how you get force in one direction. In this case, the plot is polar, however, on polar to Cartesian coordinates, the y-axis is 90 and the x-axis is 0. And if you look at it from electrical point of view, it looks like it's halfway rectified. Okay, the mechanical part here starts with a Fourier analysis of that wave shape there in figure 7 that I just showed you. I happen to use MATLAB. That's what I do all my number crunching on. When you do an FFT in MATLAB, you come up with a fundamental frequency theta. You come up with a second harmonic 2 theta, and then a steady state DC value. Problem with Fourier transforms is you lose your phase data, so you have to reconstruct that manually. It gives you the relative amplitudes, which is 1.33 and 0.69. But the phasing you have to work out on your own. That's one of the drawbacks of anyway, what you come up with on the y-axis is you get sine theta plus 0.33 sine 2 theta minus pi over 2 plus 0.69. And then for the x-axis, you get the cosine. Now the pi over 2 is actually a 90 degrees phase shift. Okay, going to the first application or implementation. This one has a single mass that's rotating counterclockwise on a variable length radius. Using a spring, it's one way of controlling the radius, which varies from nominal or unity to double. And this effectively generates the frequency harmonics we just talked about. The way it works is by changing the omega term. If you've ever seen the kitty whip at the fair, it's a device, a little car that runs on an oval shaped track. You go down the straightaway and then you hit the corner where the linear velocity is turned into radial velocity, and it generates an acceleration and whips the car out. Chris uses an actual figure 8 path or track rather than an oval, so you get more pulses, but the principle is the same. Another way of doing it that some guys have used is they use a cam mechanism to push the weight in and out as it goes around the circular path. Second implementation uses 2 separate masses on a rotating both counterclockwise on a common axis. And this is the usual Dean drive implementation that you see a lot of the advertisements, and that is the 2 masses. Uses the same equation. You got 1 sine omega t plus 0.33 sine 2 omega t minus your 90 degrees minus or plus your 0.69 offset, and then the cosine term for the x-axis. And the 2 radiuses, they have different lengths, R1 and R2, and then the masses are different. And you can trade the radius for mass and vice versa, depending on how you want to build it. Taking that theoretical half-wave rectification and superimposing the 2 equations, the red for the x equation and the blue for the y equation, you see that the blue tracks the theoretical quite closely. However, the x-axis, the red, is a vibration, which is about half amplitude. So that's the basic flaw of the initial Dean drive, is the severe vibration in the x-axis. And so there's been a few proposals out there on how to cancel that x-axis vibration. One of the ones that I've looked into is you do the same thing, only you do it twice. So you do it differentially. You have 2 masses rotating counterclockwise and a corresponding 2 masses of same value rotating counterclockwise. And so by using differentials, you can get rid of most of that x-axis vibration. And as a bonus, you get double the y value. Taking a look at the equations there, when you run them, you see the red is the two, one is the counterclockwise and the other is the clockwise, and they pretty much cancel out. So you get just a little bit of vibration along the zero axis, but where it really pays off is your two y-axis add, so you get double the value on the y direction. And that pretty much cancels out the x-axis and doubles the y, so that's going in the right direction. Looking at the equations here, it's pretty much the same, only you now have a corresponding set down here where you have a minus sign omega t, and then you have an offset pi, which is 180 degrees, plus your 0.33. Now it's a negative omega, and another 90-degree offset plus your initial 0.9, which that's the DC term, which translates to inertia. And so if you wanted to rescale this, you'd have to half it to equal the scale as the previous one. Now we're going to look into the physics book a little bit on electrical and mechanical equivalences. So we start off with a lump system. You have a mass spring system. This is basically an oscillator. You got kinetic energy and potential energy and the equations, and then the omega, which is the ratio of the spring constant to the mass. Now you go over to electrical circuits. You have a very similar system. You have the energy in the magnetic field and the energy in the electric field and the frequency of oscillation. And if you compare the equations, you'll see the equations are identical. It's only the variables that are changed. Same thing, you go down to distributed systems. You have an acoustic cavity where you have the potential energy, I got that backwards, kinetic energy first, then the potential energy, and then the omega, which is the frequency oscillation, and then your transfer speed. This C is not the speed of light, this is your speed of propagation. And you go over to an electromagnetic cavity, you have the energy in the B field, the energy in the E field, and the frequency of oscillation, where this is the C here, the propagation speed is the speed of light, which is 1 over epsilon mu square root. And all this is straight out of the standard physics book. Holiday-Resnick is fairly standard. And again, you see the equations are, format of the equations is absolutely identical, only the variables have changed. And comparing the analogy from the previous table there, looking a little closer, you see that mass M in the mechanical system is directly equivalent to the inductance L in an electrical system. The spring constant K in the mechanical system is totally equivalent to the inverse of the capacitance of the electrical system, with the frequency omega being identical for both of them. There's also other examples of mechanical to electrical analogies. Force, which is the same for both of them. The mechanical system generates force by accelerating mass. Newton's famous equation, force equals mass times acceleration. And in the electrical system, the force is generated by the interaction between the electrical field and the magnetic field. And the equation for that is the vector product of the electric field and the cross product in the magnetic field. It's also known as the Lorentz force or the left-hand motor rule. However, the force generated is exactly identical. Therefore, your M and your L are a delay or inertia term, which generates a lag in the system. And the spring constant K and 1 over C develops a lead in the system or a kick. Now going, using the same backdrop of the halfway rectified black line there for your force, superimposing the electrical on there, you now see that you get 2 pulses rather than a single pulse. You still got your x-axis and your y-axis, red and blue. However, in electrical terms, it's now half wave rectified or full wave versus half wave rectification. Dealing with the equations, the analysis starts the same as for the mechanical with a Fourier transform, only now you just have, when you do the E cross B, you only have two terms. The first one is sine 2 theta, and then the second one is the DC offset term, which represents inertia. And same problem, the FFT only gives you the relative data and the harmonic content, and you lose your phase data. So you have to reconstruct that. Going down there, you get sine 2 theta minus pi over 2, which is a 90 degrees phase shift or lag, and then you plus 1 for your offset, and x-axis is the cosine of that. And if you go to radial coordinates or polar, it's sine 2 theta, 2 times the sine theta. Now to implement that, we're taking a look at implementation there. It's only 2 parts. You have a conductive ring that carries the E field, and you have a magnetic pole which carries the B field. And so we'll delve into that a little bit. Okay, considering the implementation in electromagnetic system, in figure 11, we start running the numbers. Basically, it's 2 parts. You have an electric coil and a magnetic dipole, which is similar to what I presented here last time on the tail end of my gravity pitch, was what I call a Tesla drive. There's a few differences between that and this one. However, looking at the equations, your vector cross product for force, the general equation in cylindrical coordinates there, equation 45. I'm not going to try and get into all the equations outside of saying that it simplifies down because there's a whole bunch that zero out. The force is going to be in the radial direction, so all the other terms zero out. So when you get down to the bottom there, 46 and 47, the force vector in the radial direction is your epsilon over mu square root times vector cross product of the E field in the theta direction and the B field in the Z direction. Conversely, when you go down for the force in the Z direction, it's the E field in the theta direction and the B field in the radial direction. Now, the difference between what I showed in part 1 or part 2 of the gravity presentation, the force was in the vertical direction. This one is now in the radial direction. So we start with the E field here, just a quick run through. You have your 2 vectors, the real and then you have the cosine or the sine term, the exponential, and that has from 2 parts for the 2 points vector. And when you plot that equation on MATLAB, this is what you get. The little bar here represents the ring, and then you have E field positive and E field negative here in one shell. Now they're going out to the next shell, it's reversed. This is now the positive and this is the negative over here. And then the next shell out, it's reversed back. So every other shell rotates clockwise, and then every other one is counterclockwise. Easy way to picture that is like the agitator in a wash machine. It just goes back and forth, spins clockwise, and then the next half cycle, this just shows 1 half cycle, but the next half cycle, this reverses, so it just goes back and forth. Then we go over to the magnetic field. Now this gets a little more complicated because you have the near field and the far field. The far field is real, and the near field, you have the imaginary terms. And then you still have the exponential, which puts the cosine or sine, makes it oscillate. And you have in the radial direction, and then you have a corresponding one in the Z direction. And you take those two equations and you plot those, and this is what you get there. You have the magnetic field, which is pretty much in the Z direction, and then it spins out donut shaped because the magnet is a circular path, and then you have a node here and a node here as it works its way out. As you get further out, past 1 lambda, then you lose the near field, and you're just with the far field, so everything runs much cleaner when you get out to the far field. And same here, this is 1/2 cycle. Now the next half cycle, this thing totally reverses, all the arrows point down and spin the other way. Now, the magnetic pole was offset from the 0 point, a distance of lambda over 2 pi. The 0 point runs through here, and this is off to one side. And what that does when you put the composite all together to generate the force vectors, you see that the B field and the E field, when you cross that, you get the vector product here. On the near side of the pole, all the vectors add in the same direction, which is to the left, but over here on the other side, you see all the vectors generate a nil. So you're polarizing by moving the magnetic pole off center. You now generated a polarized wave with the vector cross product. Now the next chart here, we eliminate the E and the B, and we just have the F field in there. It's a little easier to see that all these vectors point in the same direction. And then your secondary effect, when you get out here, one wavelength is still fairly strong. And over here, they cancel, and it's pretty much 0 all on this side. Now, the one thing, the E and the B field, they switch back and forth because they oscillate. However, the vector cross product does not oscillate, it just pulses, maximum then 0, maximum 0. And it does that at twice the frequency of the driving function, which is the E and the B field. And then we get back to the equations there for the magnetic and the cross product, and you generate the E field. And from the pictures there, you see that it's polarized. Now we take and compare the second Dean drive type, which is in black, which is a slight cardioid on polar coordinates. And then the blue is the electric assumption. And there's the differences there. Okay, the 90-degree point is the y-axis and the 0 point is the x-axis. So the mechanical has more vibration in the x-axis, and then you lose a little bit here because it's negative force on the y-axis. Now going to the electric, there is no negative, and it's a little bit skinnier on the x-axis vibration. Now the counter-rotating Dean drive would be a very narrow lobe in here because the x-axis is almost canceled. Okay, on conclusions, from figure 16 there, both the mechanical and electrical forces are offset in the plus y-axis, meaning that they're polarized, and the electrical has 2 pulses per cycle versus a single pulse for the mechanical one, and it also has less vibration. However, the secret to making either system work is that the center of force and the center of mass cannot be located at the same point. That just increases the inertia or mass of the system. They have to be offset or polarized. And the narrower pulse shape in the x-axis means less vibration. However, with any system, there's real-world engineering that has to be solved to make it usable. Yeah, to get from the theoretical or the laboratory play toys to the real world, there's a whole game that you have to play to get there. Now, this is just a little refresher that from part 2, I tacked on the end to compare on the Tesla drive. This one showed a ring where the B field is now radial rather than vertical, which puts the force vectors vertical. So if you slide the B field off to one center, you can now change the force vectors or tilt the force vectors off vertical. And what that does, it functions very similar to the tilt on a helicopter rotor blade. Helicopter will generate the force in the vertical direction, and then to get forward motion, you have to tilt the rotor blade, which tilts the force vector in the desired direction you want to go. This one, you'd accomplish the same thing by moving either the ring or the pole a little off center, which would tilt the force vectors. So that would generate forward velocity. And then the vertical view here, by moving the pole over here a little bit, the force vectors will tilt. And that would accomplish a vertical, changing from vertical to horizontal direction in propulsion. And that's pretty much all I got. If you got any questions there, like I said, this was a short one, so we're not pressed for time. And let's see, I'll get to stop the sharing here. And we'll go back to taking questions.
Well, short one, but still wonderful. Mike, let me do this. I want to put this on gallery view. Everyone, please give Mike a big hand for running us through the Dean drive, the variants. Yeah, that was wonderful. And again, a follow-up to the earlier things you presented. So thank you very much for going through that for us.